So in this video, I'm just going to talk a bit about some of the terms and definitions that we need to look at our ODEs. And the most important one by far is known as the Lipschitz condition. The Lipschitz condition reads, a function ft comma y. Now note, all our differential equations we're dealing with at the minute are going to be dy dt is equal to ft comma y. So that's why it's so important. It's said to satisfy a Lipschitz condition in the variable y on a set D, which is subset of the real x and y, the real squared, if a constant L exists with the property that ft comma y, y1 minus ft comma y2 is less than or equal to our Lipschitz constant y1 minus y2 whenever y1 and ty2 are elements of the domain we're interested in. The constant L is called the Lipschitz condition of f. So that's our definition, and it is very important. But really what it's saying is every function can be bounded by a constant plus how big a step you want to take. And we're going to come to this again and again, but in numerical methods, we have to make a step in the x direction or the time direction. And so what it's saying is, if we have a point t1 and a point t2 has a corresponding y1 and y2, the jump between those two is continuous. It's really a continuous definition. So let's do a really, really simple example. ft comma y is equal to t plus y. How do we show this satisfies the Lipschitz condition? So what we have to do is the absolute value of t plus y1 minus t plus y2. Well, that's easy enough. The two t's cancel, which gives us y1 minus y2 multiplied by 1. That's our Lipschitz constant. Let's do another one. ft comma y is equal to 2y. So our Lipschitz condition would be 2y1 minus 2y2 2y2 is less than or equal to 2y1 minus y2. So here L is equal to 2, here L is equal to 1. Now, as they become more advanced, and we do in class, you have to do a bit of jiggery-pokery. But really what it's saying is, you have a bound on your solution. You cannot do an infinite jump within the domain you're interested in. So, this leads on to the definition of a set D, which is a subset of R, so once again, that's a domain D, is said to be convex if whenever there are points t1, y1, t2, y2 belong to D, the point 1 minus lambda t1 plus lambda t2, 1 minus lambda t also belongs in our region for lambda between 0 and 2. This seems like an obvious statement, but it's one that we have is, so that's t1, y1, and that is t2, y2, and all the definition is saying is that we can draw a line between the two, and the line is in our domain. So once again, we need this because when we approximate our numerical solutions, we assume a linear step between the points, and therefore it should be in our domain. Once again, this is just making sure our solution doesn't go to infinity. These two are kind of the same thing. Now, L is a very general thing, so maybe there could be a theorem that upper bounds the L. And so that's our first theorem here. We won't do the proof, but suppose ft comma y is defined on a convex set, D, which is contained in the real number squared. If a constant A exists, then A is less than or equal to the absolute value of the ft ty dy, then f satisfies the elliptic condition on D. Really, once again, it's saying is no infinite jump. And we need that. This then leads to, suppose, now, throughout this, we're talking about f. But no, f is also talking about the derivative of y, and therefore it's saying that the derivative of y is not quite continuous, but observes that it doesn't go to infinity. So the theorems oppose that on a domain D, which is between a and b and minus infinity and plus infinity, so it's a very big domain, less than fty is continuous on D in the variable y, then the initial value problem has a unique solution. All this is to make sure we have a unique solution. Why do we need a unique solution? Because if there are two solutions, well, there's no point approximating. Now, when in biomaths you talk about bifurcations, which sounds like there are two solutions, a bifurcation is not two solutions, it's two possible solutions, but each are unique given certain conditions. Next, just more about our initial value problems. If we have an initial value problem, dy dt is equal to ft comma y over the domain a less than or equal to t less than or equal to b, where our initial condition y of a is equal to alpha, it is said to be well posed if it has a unique solution. If it does not have a unique solution, we shouldn't even attempt the problem. And for a small epsilon, so that's always think of epsilon or a tolerance as a perturbation. There's a positive constant, k epsilon, or k lowercase epsilon, with the properties that whenever epsilon is 0, the absolute value is less than epsilon, and we have some delta t on our domain, there is a unique solution. So by adding a small perturbation onto our original equation, we get a new answer. But that new answer is within reason of that perturbation. So what it's saying is, if you do something small, it shouldn't matter too much. Now, of course, there are bifurcation points, but really all once again is saying not infinite.